The Mechanical Engineering Laboratories present Free and Force Vibrations, Experiment V1. Introduction. Free vibrations happen in many structures where the structure vibrates at its natural frequency. Forced vibrations may occur where an external force causes the structure to vibrate at any frequency, including the natural frequency of the structure. When the forced vibration frequency equals the natural frequency, the structure will resonate at a potentially dangerous amplitude and might damage the structure. History has several examples of this problem. These include the collapse of the Tacoma Narrows Bridge in the US in 1940, and the temporary closure of Millennium Bridge in London between 2000 and 2002. Designers need to understand how free and forced vibrations affect structures, the magnitude of the oscillations they can cause, and how to reduce them. The objectives of this lab experiment are investigating the effect of added mass on the natural frequency of the simply supported beam, studying the relationship between oscillation amplitude, phase lag, magnification factor, and speed ratio, understanding the damping effect on the oscillations in a simply supported beam assembly, to show how an auxiliary oscillating system can help to absorb the vibrations of a simply supported beam, and to show the three key frequencies of the 2 degrees of freedom system and resonance at the upper and lower system natural frequencies. Apparatus description. In this experiment, Techquipment's free and forced vibrations apparatus uses a metal beam held as a simply supported beam. The apparatus has 2 parts. A left-hand section containing the controls and other electrical circuits, and a right-hand window containing the experiment parts, in addition to VDAS system. The experiment window holds a metal simply supported beam and a low friction bearing that works as a pivot to hold the end of the beam. A motor fixed to the beam has 2 rotating discs, each of which with an eccentric rotating mass. This combination forms an exciter, providing the forced vibrations. The exciter has sensors to measure motor speed and rotational position of the eccentric mass. This non-contact sensor measures the beam displacement by detecting the distance from a powerful magnet under the beam. This gives a measurement of the beam displacement at this position. This sensor has an important advantage. It has no damping effect on the oscillation because there is no physical connection with the beam. You may connect a dashpot damper under the beam for experiments with viscous damping of the vibrations. The dashpot damper used in the equipment uses fluid to provide viscous damping when connected below the exciter. The dashpot damper disc has 2 sets of holes. As you turn its metal shaft, the 2 sets of holes move relative to each other. You use this to adjust the damping. When the holes are aligned, they are fully open and the damper produces minimum damping, as the fluid can easily pass through the holes. When the holes are fully shot, it produces maximum damping. When the holes are half open, it produces a medium amount of damping. You may also attach a vibration absorber to experiment with an alternative method of reducing oscillation amplitude. The control section has a display showing the speed of the exciter disc when used for forced vibrations. Other controls include the set 0 adjustments for the displacement and acceleration sensors. Make sure that the set 0 lights are off during the different steps of the experiments. There are 2 special metal calibration blocks available with the equipment. Students do not need to use these blocks to calibrate the sensor. However, if necessary, you may need to make some small adjustments to the set 0 controls so the VDAS trace is at the center of the chart. The equipment accessories include a set of masses and a holder. These masses can be fixed under the exciter to show how the added mass affects the beam oscillations. VDAS, which stands for Versatile Data Acquisition System, is an essential data acquisition system to provide real-time traces of the oscillations, automatically calculate data, create charts and tables of the collected data, export your data for later processing in other software. You need to be familiar with the VDAS screen. This icon is to initiate communications with the device and to start recording the oscillation. This icon is to record data. In this section, student can select the experiment setting, mode type, free vibration or forced vibration. In this section, the student can include the vibration absorber and the value of the added masses to the system. These sections are used to measure and enter the experimental values of the natural frequency in addition to present the system calculations of important parameters. Measuring the natural frequency. To measure the natural frequency of a specific oscillation, you need to freeze the oscillation in VDAS first. Use the cursor tools in VDAS to measure the distance between oscillations. This will give the measured natural frequency of the system in the cursor section on VDAS screen. If necessary, you can change displacement channel 1 setting to see the reading clearly. In some cases, you need to enter the measured natural frequency values in the measured value cell in the natural frequency section on VDAS screen. You can compare the measured value with theoretical value calculated by VDAS. Measuring the amplitude. To measure the oscillation amplitude or displacement, use the two Y cursors to find the distance between the center and the peak of the oscillation, which is the delta Y. This measured value should be entered in the Trace Measurement section on VDAS screen. Measuring the phase lag. In forced vibration, the phase lag can be found by measuring the distance between the x-axis cursor at x equals 0 and the x-axis cursor at the first peak. This value is calculated by VDAS and shown as delta angle in the cursor section of VDAS. The delta angle value should be entered as the phase lag value in the Trace Measurement section on the VDAS screen. Experimental procedure. Experiment 1. Simply supported beam. Added mass experiment. The first step is to set the experiment window as shown here. Before starting this experiment, make sure that the VDAS system is set using the following values shown in Table 1. Create a blank results table similar to Table 2. Alternatively, VDAS automatically creates its own data table as you record data. First run will be performed with no additional mass. Therefore, set added mass value in VDAS to 0. Start VDAS by clicking on the Initiating the Communication with the Device icon and use the flat of your hand to slap the top of the exciter. Then stop VDAS immediately to freeze the oscillation on the screen. Use the cursor tools in VDAS to measure the distance between oscillations. This will give the measured natural frequency of the system in the cursor section on VDAS screen. You need to enter the measured natural frequency values in the measured value cell in the natural frequency section on VDAS screen. You can compare the measured value with theoretical value calculated by VDAS. Now record the data. Don't forget to do this after each step. The second run. Attach the mass holder with no masses. If necessary, readjust the set 0 control in VDAS. Enter the mass holder value, 200 grams, into the added mass field. Again, find the measured natural frequency similar to what you did in the first run. The third, 2/7 runs. In each of the following 5 runs, add one mass of 400 grams and repeat measuring the natural frequency as you did in the previous runs. Remember to update the added mass field in VDAS. Please note that you might need to readjust the set 0 control before finding the natural frequency. Fill Table 2 with the required measured and theoretical values after finishing each run. Experiment 2. Simply supported beam, damping. Part 1. The first step is to set the experiment window as shown here. Fit the damper metal shaft alone under the exciter. Set VDAS as shown in Table 4. If necessary, readjust the set 0 control. Find the measured natural frequency, free vibration, as shown in Experiment 1, and enter the measured values into VDAS. Part 2. To find the damping ratio, follow these steps. Adjust the time base to 500 milliseconds. Start VDAS and slap the top of the exciter to start the oscillations. Allow VDAS to record at least 6 seconds of oscillations, then stop VDAS. Use the horizontal scroll bar on the chart to show only the cleanest section of the waveform. You should see that the oscillations are underdamped. Use Channel 1 tools to choose the underdampened model and fit the data. VDAS will update its damping parameter data section, including the damping ratio. It should produce a model with lines fitting the waveform. Part 3. Change VDAS to forced vibrations and make sure it has the same measured natural frequency in Part 1, so it can calculate the speed ratio for you. Set VDAS as shown in Table 5. Start VDAS and press the exciter motor start button. Adjust the speed slowly to match the speed ratios shown in Table 6. At each step, wait for up to a minute for the oscillations to stabilize, then freeze the oscillation on the screen to measure and record the displacement amplitude and phase lag on Table 6. Repeat this procedure for all speed ratios in Table 6. Notes: you can change Channel 1 displacement to measure the amplitude properly. The phase lag can be found by measuring the distance between x-axis cursor at x equals 0 and the x-axis cursor at the first peak. Now, attach the damper dashpot and adjust the piston disc to fully open position for the lowest damping coefficient and repeat the test. Repeat the same procedure, parts 1, 2, and 3, for fully open damper, half open damper, and fully closed damper, and fill in tables 3 and 6. Please note that for each case, we have new values of natural frequency and damping ratio. Save your previous work and make a new file for each new case using VDAS. Experiment 3. Simply supported beam vibration absorber. Anti-resonance. Disconnect the dashpot damper from the beam. Fit the vibration absorber here. Set the masses of the vibration absorber to their innermost positions so they form a basic load, but cannot vibrate. Each mass is 14 millimeters thick, so their mass center is at 7 millimeters. Add 2 masses to the exciter using the mass holder. The total added masses with the holder is equal to 1,000 grams. Set VDAS according to Table 7. Using forced vibration, slowly increase the speed to find the natural frequency of the system with the added mass of the vibration absorber. Write down the frequency and oscillation amplitude using Table 8. Adjust the masses of the vibration absorber using the calculated theoretical position of the masses to cancel the natural frequency of the system. Remember that the theory calculates the distance to the center of the mass. Using forced vibration, slowly adjust the speed again until you reach the natural frequency. Note that the main beam oscillation amplitude is near 0. The system is now at anti-resonance. Record the frequency and oscillation amplitude in Table 8. Slowly adjust the speed up and down from anti-resonance to see the two new system frequencies where both the main beam and vibration absorber oscillate at relatively high amplitudes. Enter these two frequencies and their amplitudes in Table 8. Absorber masses set at the distance for antiresonance. Adjust the exciter speed slowly in steps of around 0.25 Hz from around 12 Hz to the maximum speed that the exciter can deliver. At each step, use Table 9 to record the amplitude of oscillation. Now you have all you need to analyze the experimental results.